Scan the mic, you can still hear me. It's a pleasure to welcome you all to the Don P. Giddens Inaugural Professorial Lecture. And today we're here to honor Misha Kazhdan. Misha is a professor of computer science and a member of the Hopkins community since 2004. His research focuses on image and geometry processing, particularly in surface reconstruction and shape analysis, and on developing data structures and algorithms that are used to efficiently reconstruct high-resolution surfaces from large point clouds and new techniques for analyzing the geometry of 3D shapes. He has developed numerous software programs, including Poisson Recon, a program that was used by NASA in the reconstruction of the Martian landscape, using data acquired by the Curiosity rover. Pretty exciting work, pretty interesting breadth of applications, actually. And so I'm very, very glad that we're here today to celebrate his achievements and to learn more about his research and its applications. I will also say, as I always do, that this inaugural professorial lecture honors one of my predecessors, Don Giddens, who was the 5th Dean of Engineering at Johns Hopkins, where he was also professor of mechanical engineering. Giddens' career has been defined by his commitment to research and education. And so in addition to recognizing Misha for his research, we're also honoring him for his contributions as a teacher and mentor. And of course, the promise that we see in Misha for the future. And with that, it is my pleasure to introduce the head of the computer science department, Randall Burns.
Thank you, Ed. It is great to be having these professorial lectures and a nice way to come back from COVID. I could give biographical information about Misha, but that is not my job. I will have a couple remarks about Misha, which is Misha and I have been at Hopkins together. He came in 2004 and I got here in 2002, and we've had many relationships. We have been colleagues, we've been friends, we have co-advised PhD students. I have been a student in his class. He had the unfortunate circumstance of having me as a mentor for a while. And it's just a really rich relationship that makes me very excited. And so I have the privilege to introduce Tom Funkhauser, who's going to have some pre-recorded remarks. Tom was Misha's PhD advisor, and they worked on something called the Princeton Shape Benchmark back then, which has been a phenomenally important piece of work, which is indicative of the type of work that Misha does, which is he's a leading mathematical thinker in geometry processing. He has 5 papers with more than 1,000 citations. So he does deep, interesting, meaningful work that is also practical. Tom Funkhauser was a professor at Princeton from 1998 to just recently. He is now at Google. Tom did groundbreaking work in acoustics and in graphics. He has been the chair of SIGGRAPH. He won the SIGGRAPH Lifetime Achievement Award and is just an eminent figure in the community. And so with that, I will give you to Tom.
Hello, my name is Tom Funkhauser. I was Misha's PhD advisor at Princeton. I'd like to introduce you to him by giving a brief overview of his research. Misha's early work focused on content-based retrieval of 3D shapes. At the time of his PhD, databases of 3D shapes were just starting to become available in online repositories. Our research group recognized this as a potential research opportunity and built the first ever shape-based search engine. Misha in particular developed the core shape descriptors that drove the similarity matching between 3D shapes. His pioneering work on that problem laid the groundwork for designing and evaluating shape descriptors and led to hundreds or maybe even thousands of follow-up papers. Today, 3D shape retrieval is a research subfield with an annual meeting of its own. After graduating with a PhD, Misha focused on 3D surface reconstruction. Given a set of 3D points with estimated surface nulls, the goal is to produce a solid object whose surface best fits the input data. Methods at that time were heuristic, and thus did not provide guarantees or globally optimal solutions. To address this problem, Misha introduced Poisson surface reconstruction, which solves for the 3D scalar function whose value indicates outside of the object and whose gradient fits the vector field defined by the input positions and normals. Misha implemented efficient multi-grid solvers to make this theoretically elegant solution also practical. That implementation is still in widespread use 25 years later. It won the first ever software award at the Symposium on Geometry Processing in 2011, and the accompanying paper won the first ever Test of Time award at the same conference this past year. Misha later went on to significant contributions to many other research problems, including 3D registration, symmetry detection, and shape analysis. In almost every project, he proved theoretical properties of the proposed methods and also demonstrated practical applications, often in a wide range of fields, such as image editing, geometric modeling, and medicine. At this point, I could not be prouder of Misha. Congratulations to him for becoming a full professor, and congratulations on an outstanding career.
Thank you, Tom. Misha?
Thank you, Ed, Randall, and Tom for your kind words. It's a great honor to be promoted to full professor, and I'm grateful and humbled by the recognition. Before jumping into the lecture, I thought I would take the opportunity to talk a bit about myself, where I come from academically, and how that informs the way I approach research. I grew up surrounded by mathematicians who inculcated me from a young age that mathematics was as much about beauty as it was about truth. The ideal, as I heard it, was not so much to solve a problem or to demonstrate that a claim was technically correct. It was to come up with an idea and intuition that was so elegant in its simplicity that it once elucidated and opened researchers' eyes to new possibilities. Given my upbringing, it wasn't surprising that I entered university as a math major. Perhaps a little less expected was that I also unofficially majored in sculpture. Where this came from, I'm not sure. But I do know that one of the things that attracted me was the aspiration of taking an elusive fragment of an idea, something seemingly intangible and inexpressible, and transforming it into something concrete. The informal double major lasted through my first years of graduate school until a certain amount of questioning convinced me that I would be better suited melding math and sculpture by pursuing computer graphics. Looking back, I recognize the importance that the elegance of a solution and its ability to generalize beyond the problem at hand has held for me. It's what excites me most about the work of others and what motivates me in my own. I also see the desire to give form to concepts reflected in a need to transform research ideas into computer code, a sort of proof is in the pudding approach where the measure of whether an idea has been made concrete is an executable that puts it into action. Focusing on today's talk, it's hard to miss the role that math has played in my research. Techniques from calculus, representation theory, differential geometry, linear algebra, real analysis appear with some regularity. Clearly, mathematics provided me with a valuable tool set for approaching problems in computer science. But a nagging question remained. Could the tables be turned? Could my perspective as a computer scientist provide an intuition for approaching math problems? In today's talk, I would like to describe a work that I hope answers the question in the affirmative. So in this work, we're going to look at the question of smoothing signals, smoothing geometry. And to make this concrete, we need some measure of what it means to be smooth. And sort of the standard approach is something called the Dirichlet energy. The measure of the change of a function is its gradient. So you take the magnitude of your gradient and you sum it up over your domain, you integrate it. That tells you how much variation there is in your signal. With this in hand, smoothing becomes a process of gradient descent. You have some candidate signal, you establish or compute the gradient, sort of the perturbation you would need to apply to the signal in order to make it more energetic, and you go in the opposite direction. Then you get a new signal and you repeat this process. This can be applied to images. It can be applied to signals on non-Euclidean domains, for example, textures on surfaces, and recognizing that when you have a surface embedded in 3D, you already have an inherent signal. The X, Y, and Z coordinate functions are functions on the surface. You can smooth the surface itself. This last one has a name. It's been around in the mathematics community for almost 100 years, is mean curvature flow. And the idea is to deform the surface by pushing it in the normal direction, or the negative normal direction, with a speed proportional to the mean curvature. Now, if we look at this in the concept of curves, things behave really nicely. You have the curve, you have its normals, and this indicates the directions it's going to want to go. In general, this flow, mean curvature flow, tends to collapse things. To be able to see what's going to happen, we're going to need to zoom in. And this was proposed in '84, where you zoom in on this object as it's collapsing to try and see how it's collapsing. But what's known is that for the case of the curves, this will collapse very nicely. As you zoom in on this thing collapsing down, as it gets smaller and smaller, it's going to look more and more round. Unfortunately, this doesn't hold for surfaces. So over here, I've taken that same dumbbell curve and I turned it into a surface of revolution. I've even showed a cutaway. What happens with the dumbbell curve? Well, it has this arm, and the arm has no curvature. And since it has no curvature, it just waits. It's very patient. Waits for the two ends to sort of come together and drag it inwards. When we look at the surface of revolution, that profile, that straight profile, becomes part of a cylinder. That does have curvature. And as a result, it's a little greedy, it's a little impatient, and it doesn't wait for anybody. It just goes off and does its own thing and collapses inwards. And this is called a neck pinch singularity. This has been known, again, in the mathematical community, that non-convex shapes will do this. So our goal will be to try and take a computer science perspective to this problem and try to adapt the flow to avoid these singularities. Right? And again, here you have the cutaway of that dumbbell curve. Here you have some other surface. And this is the type of results we're looking to get. Now, if you ask a computer scientist, or you tell a computer scientist, I have some process that's resulting in a singularity, what do you think is going on? The first thing they will tell you, division by zero. Right? And so that's our intuition. That's our community's intuition. And that's what we're going to do. We're going to go in search of this division by zero to see how this thing is collapsing, why it's collapsing. In order to do this, I need to build up a little bit of a framework. So let's start with that. We have some initial surface M, and we're looking to deform it, which is to say we're looking for a family of maps evolving over time, giving the new positions of the surface, mapping the old positions to their new positions in space. The problem with this from a computational perspective is that the space of functions is infinite dimensional. You can't really work with that. So what you do is the standard approach. You don't work with all functions. You choose some basis. And for the purposes of this talk, it makes no difference what the basis is. You just choose a finite basis. And now signals that you're going to represent are just linear combinations of these basis functions. Now, in our case, we're looking for a time evolving function that gives us not one, but three values. So we're looking for coordinates that live in 3 dimensions and change over time. But that's our description of the evolving surface. With this in hand, the flow is described by a partial differential equation relating the temporal derivative of the coefficients with their current values. And in particular, what you have are two matrices, the mass matrix and the stiffness matrix. Again, very well known concepts. The mass matrix says take your two basis functions, multiply them, integrate them over the domain. The stiffness matrix is very similar. It says take your two basis functions, take their gradients, take their dot product, and integrate that over the domain. For our purposes, we're going to look at two components of these calculations. You have d mu t. This is the measure. This is something that allows you to calculate the size or the area of a region around a point. We're integrating, so we need some notion of the size when we're doing this. That's given to us by the measure. We also need a gradient, and that is a measure of change. In this case, we have a two-dimensional surface. You want sort of two components. Typically, what you'll do is you'll pick some orthonormal basis, and you'll ask how much is it changing in this direction, how much is it changing in that direction. Okay. So going back to our partial differential equation, we have this relationship between the temporal derivative of our coefficients and their current values. Of course, we can't really do this at infinite precision in time either. So we discretize this. We replace our derivative with just a finite difference. And then we start gathering terms, getting an equation, a linear equation that relates the coefficients at the new time step, the information that we're after, with the current state of the object, which is what we have. And that gives a very simple algorithm for mean curvature flow. You compute your mass and stiffness matrices, you solve for the next time step, you advance, you get new mass stiffness matrices, and you compute the new coefficients. So where's the division by zero in all of this? And how are we going to fix this? So one thing we should keep in mind is as we're doing this evolution, we have some patch on our initial surface, and that'll map to some new patch. It'll get distorted in the process. For example, it'll get stretched and scaled. What happens to the two components, what we talked about before, the measure and the gradients? Well, the measure will scale. If we take a patch of one area and we match it to a bigger area, the measure will scale correspondingly. What happens to the gradients? The gradients describe the change over distance. So if we scale our domain, the values of the function, the difference in the values is the same, but it's happening over a larger distance. So the gradients, the derivatives decrease, or they are reciprocally related to the scale. When everything is good, the scaling of the measure and the scaling, or the inverse scaling of the gradients cancels. When that's not the case, this is our division by zero. So let's see how this happens. We have a particular point P on our initial surface, and that's going to get mapped to some point Q on our evolved surface. We can also draw a little circle around P, and that's going to map to some sort of ellipse around Q. Now, for this ellipse, we can compute the principal axis and the radii of this ellipse in the two directions. And what happens is there are corresponding directions around P that'll get mapped. So we'll have a direction U1 that'll map to direction V1 on the evolved surface, and it'll scale by the associated radius. And we have a direction U2, again, orthonormal, that'll map to direction V2 and will scale by that radius. How does this affect our computation? Well, we had our measure, and we can describe the area of a patch on the evolved surface. What is that? Well, it's the area of the original patch scaled by these two scale factors. It's sort of like if you take a rectangle, you scale by one value in one direction, and in the other direction, the total scale is the product of the scale factors. What happens to the derivatives? Well, if we had the partial derivative across UI, along in the UI direction, that direction is going to get stretched by the radius. As a result, we'll see a drop-off of 1 over the radius affecting the new gradient, or the new partial derivative in the corresponding VI direction. What does this mean for our calculations? Well, so we have our mass matrix, and what we said is you take your functions and you integrate them over the evolved surface. So you integrate them with respect to the notion of size or measure on the evolved surface, but we can also do the integration over the original surface, and the measure just needs to be scaled. Right? So instead of taking the original measure on our starting surface, we will see how big is that patch on the evolved surface, and that's how much contribution we have around that point. Okay, that seems reasonably stable, nothing bad happening here. Let's do the same thing for the stiffness matrix. So again, we want to integrate the gradients over the evolved surface with respect to the measure. We can play the same trick. We can do the integration over the original surface, scaling the measure to account for the change in area. Now we have these gradient terms, right? So we want to take the partial derivative of our function bi with respect to direction v1, multiply that times the partial derivative of our function bj with respect to v1, and add to that the same product with respect to direction v2. Okay, that's the dot product of the gradients expressed in the evolved system. But again, we can relate the gradients in the evolved system, or the partial derivatives in the evolved system, or the deformed state, to the original state. And there, what did we say? We said that the partial derivative with respect to v1, that's the same thing as the partial derivative with respect to u1 scaled by 1 over the radius, accounting for the fact that there's a scale which makes partial derivative become smaller. So we get this expression all in terms of the quantities at the initial state. We can do a little bit of cleanup knowing that we have some things in the numerator and denominator. And at this point, as computer scientists, we're ecstatic. We have a fraction. And the moment we have a fraction, we have the opportunity for division by zero. So let's take a look at these fractions. What are these fractions? These are the ratios of the scale factors. When you have a circle and it evolves into ellipse, say it's getting long in one direction and skinny in the other direction, one of these ratios is going to go to 0. The other one is going to blow up. And that's certainly going to cause some computational headaches. Okay, so now that we've identified this, how do we bypass this problem? We'll do something very stupid. We'll just say, you know, the whole problem comes from the fact that our circle is mapping to an ellipse and not a circle. So let's pretend it maps to a circle. It doesn't have to be a unit circle, it can be some other circle, but let's pretend it maps to a circle. The only question we have to decide is, what should the radius of that new circle be? And a very natural choice is, well, it should be the average. Right? Oh, sorry. There we go. Turns into a circle. It should be the average of the radii, except for when I say average here, I mean the geometric mean. scale factors act multiplicatively. So if you want to average them, the very natural thing to do is take their geometric mean, not their arithmetic mean. So that's what we'll do. Okay, so we have a new notion of scale, this little tilde thing. How does that affect our calculation? Well, we can try and compute the mass matrix with respect to these new scales. Again, we're multiplying our measure by the product of these scale factors. But these are the geometric means of the original scale factors. So when we multiply them, we'll just get the original scale factor. So we get back exactly what we started with. In fact, nothing has changed for the mass matrix. What happens to the stiffness matrix? Well, we have the ratio of the scale factors, but the ratio of the scale factors is now 1. We've made them isotropic. This all cancels. And what we're left with is just the stiffness matrix with respect to the original time step. So we get a very simple algorithm. In fact, simpler than mean curvature flow. We do exactly what we did before, but we hold the stiffness matrix fixed. We never change it. So less computation. So how does this work in practice? At the end of the day, we are empiricists. So what's going to go on? Well, we had mean curvature flow. You update the mass and stiffness matrix with each time step. You also have the conformalized mean curvature flow, where you pretend things are isotropic, where you hold the stiffness matrix fixed, and it's just the mass matrix that evolves. To complete the picture, we could also look at something called heat flow, where you just hold everything fixed, the mass and the stiffness matrix. And you can ask, how do things behave under this flow? We'll start off with this dumbbell shape. And here's mean curvature flow, the first couple of steps. You see that it's smoothing, but a neck pinch singularity is forming, and it can't do anything. The arm of this barbell has collapsed into itself, and that's it. We're done. We can look at heat flow. Heat flow uses the mass and stiffness matrix from the original time step. They can't blow up because they're fixed. They're just the same ones throughout the whole flow. So it behaves very well. You can run this as long as you want. As it collapses, you can zoom in to see what's happening. And it turns out into these sort of long, skinny, elongated figures. This is not really so surprising. Sort of from a mathematical perspective, you're projecting your coordinate functions onto the Fiedler vector, whatever. It's understood, but it's not particularly pretty. The conformalized mean curvature flow, again, starts off by smoothing, but then as you collapse, seems to be getting rounder and rounder, much like Grayson's work on curves. We can look at other curves, other surfaces, like the brain or the Lucy model or the octopus, and we see the same thing. Mean curvature flow forms these neck pinch singularities and stops. Heat flow can be run indefinitely, but doesn't give you particularly interesting results. And conformalized mean curvature flow seems to be converging towards some nice round geometry. So we can try and evaluate this. And the first thing we want to ask is, does it converge? And one measure of convergence is look at this evolution and look at how much the points are changing with each iteration. If it's converging, you're expecting these points to move less and less with each time step. And indeed, we ran this on a bunch of models, and you find, over these 24 models, that all of them converge. I would almost like to say to numerical precision. It's not quite numerical precision. There is room for a little bit of wiggle in here because of Mobius group, but let's not get into that. Okay. We also saw that it seems to converge to a sphere. Does it? That's a reasonable question. So what we can do is we can take the surface we get at a particular time, compute its center of mass, and look at the average distance of points from that. That would be the radius of the sphere for good, and then study the variance of the points from this actual radius. And again, we find that there seems to be this convergence towards the sphere. Now, the last thing we would ask, and this is again, sort of looking at things from a little bit from the mathematical perspective, what we did in our evolution is we modified the flow, pretending as though we're isotropic, as though the scale at each point was uniform. So we're taking circles to circles. So one way to measure this is at every point, take the ratio of the scale factors. And integrate that over the surface and see how much that deviates from 1, or how close is that to 1. And this gives you this measure of conformality. And we see that it's interesting. If you look at the beginning of the curve, it's clear that the evolution is not conformal. That is to say, in the middle, the shapes that you are getting are not isotropic deformations of your initial surface. It is only in the limit that you're getting this. Okay. So sort of going back, we were looking at mean curvature flow. This is a well-studied problem in mathematics. One can talk about it in terms of normals and mean curvature. One can talk about it in terms of smoothing. One can talk about it in terms of area minimization. One can relate it to practical applications like the formation of soap bubbles. It's exciting and it's really elegant, but it collapses or forms these singularities. So again, taking the approach that singularity is the same thing as division by zero, it's not that we solved the problem, but we've sort of identified what to look for. And once you know what you're looking for, things tend to get easier. What's surprising is, well, so we get a better behaved flow, right? We see that this does converge and converge nicely to a sphere in a conformal way. The algorithm is actually simpler. It's not harder. We just fix one of the matrices instead of letting it change. What you can show is that if it converges, it's going to converge to a sphere. And if it converges to a sphere, it has to be conformal, but we still don't know if it's going to converge. I mean, computer scientists can't do all the work for mathematicians. So that's where we are. So taking a step back, working on this project with Jake and Miri was a wonderful opportunity. So Jake is a professor of mathematics at Hebrew University. And if there's one thing working with mathematician teaches you, is that you have to earn the right to be wrong. Because initially you're just saying nonsense. And they'll tell you this. Luckily for me, Jake is sort of the uncommon breed of patient mathematician. So that was good. Miri is a professor of computer science at the Technion, and working with her is always a learning opportunity. She's an expert in geometry processing, and she expresses herself with such effortless clarity that I'm actually kind of at a loss for words for describing. It was great working with her. More generally, I feel like I've been really lucky. I've had the chance to work with a fantastic set of colleagues. Some of them are students, some of them are peers, some in this discipline, some of them are outside, but all of them bringing their own perspectives to the problem and all of them helping me to find my own. But really, where I feel most lucky is in the set of mentors I've had along my way. It's not that they taught me to do research. Some did, and some did not. It's that they stood as role models for the fact that being an academic was more than being a researcher. It was about creating relationships, contributing to the community, and enabling and promoting the success of others. I was inspired by them and inspired to be more like them when I started, and I continue to be inspired and aspire today. Thank you.
Thank you, Misha. Questions?
Doesn't work well. It collapses.
If it's, I'm sorry?
A torus.
Oh.
Yeah, it doesn't work well. Correct. That's a good question. There's a lot of questions. To me, this work more opens questions than resolves them, and I don't know. I don't know. I don't know what happens if you're on torus. I don't know what happens if you're a surface that's living on some other manifold and you're doing mean curvature within that manifold, maybe not an Euclidean. Don't know.
Yeah, I first I'll echo the privilege to do some research with you and go as a student. And I always felt like I was learning more maybe I was teaching. I think of a question. Looking at the hand you used as an example. Yeah, it gets smoother, but it also somehow the fingers do weird things, and maybe that's inherent in what we're looking at. What happens if you try to constrain flow, for instance, so that you're also preserving the ball?
So this is well studied.
I mean, we have this often in surface simplification.
Yeah.
Have you looked at that?
I have not. There certainly have been works that look at volume preservation under the action of mean curvature flow and sort of perturbing what you would sort of the natural inclination just move in the normal direction in such a way that the overall volume is preserved. This is studied, I believe, if you think of mean curvature flow as an area minimizing flow, it's closely related to a squared area minimizing flow. But I hesitate to say more. There's one more.
Told I'm supposed to use the microphone so that
Ah.
I guess the people on the live stream can hear. Okay, so I'll also repeat the question. Go ahead, Fadil.
You're saying of mean curvature flow? So mean curvature flow, no. So I think that's wrong. You can't, because this is a problem in the analytic formation of mean curvature flow. It's not a question of discretization. It's not that if you somehow use some other technique for doing it, you'll bypass it. The formulation of mean curvature flow will naturally create these singularities, and there's no getting around that. In fact, what is known is that convergence of mean curvature flow is only for weakly convex surfaces. Really, beyond that, it's not that it has to collapse, but this is a property not of the discretization, not of the basis stuff, with the actual PDE itself.
So if I may, I'm gonna ask one question because I'll say the following. Your talk was so clear that it gave me the impression that I understood something. And so I'm going to ask a question. So, and maybe you answered it. You say that you replace the scaling factors by the geometric mean of the scaling factors, and then you, so to speak, solve the problem. But you must have given something up. What did you lose? Is it just the non-conformality at the early stages? What did you give up? You must have given something.
So mean curvature flow has some nice properties, some nice analytic properties. For example, if you have a surface that is not self-intersecting, you are guaranteed that until mean curvature flow collapses, it will never self-intersect through the course of the evolution. That's not the case here. You certainly don't have that guarantee. It's also the case that mean curvature flow came from the process of simulating the formation of soap bubbles. And what you could picture is, if I have two circles and I create a soap bubble between them and I start pulling them apart, a singularity has to form. Nothing has to pinch off and turn into two soap bubbles. That's what happens. This model doesn't allow that. It allows it to get arbitrarily thin. It's not minimizing the surface area. It's optimizing over something else.
Thank you. Well, I think what we're going to do next is actually three things. Number one, thank you again for really a wonderful presentation, and congratulations. And as part of this event, I'm going to present you with this souvenir.
Thank you.
Your initial professorial lecture.
Thank you.
Congratulations.
Thank you very much.
And then last but not least, for those of you who are actually physically here, it's not quite like it was before COVID, so we can't quite have a reception, but, and this is, I'm saying this as much for the people who are listening via live stream, what you don't get, and what the people here do get, is a cupcake on the way out of the room. That's perhaps the most important thing today. So again, congratulations. And
Thank you very much.
thank you all very much for joining us.